Welcome everyone. Welcome back to the international workshop on condensed matter solitons. This is the first afternoon session on the second day of the conference. In this session, we have, by the way, I'm the Yong Il-shin from Seoul National University and then do a chairperson in these sessions. In this session, we have two speakers. So the first speaker is Professor Jae-yoon Choi from KAIST. Let me introduce him briefly. Jae-yoon did his PhD in Seoul National University in 2009. And then he moved to the Munich and the Max Planck Institute and working with the Immanuel Bloch group. And over there, he did a fantastic work on the many-body localization in Bose-Einstein Hamiltonian. Over there, he showed that the first realization of the many-body localization there. And then he moved to the KAIST in 2017 and then started his own group there. And he recently successfully building up his own apparatus of lithium-7 quantum microscope machines and then doing that excellent work. Today, he will talk about that spin-off Bose-Einstein condensate where he studied about universal coarsening dynamics in the ferromagnetic condensate there. So please welcome him with a big hands. Okay.
Okay. I hope everybody can see my slide and my voice quite clearly. First, I'd like to thank to the organizer and of course, thanks for the great invitations, great introduction. I like this sort of interdisciplinary workshop that I can introduce our, although it is like different platforms using atomic gases, but in terms of physics, it touches very commons such that we can actually discuss a bit more. Before starting talk, I'd like to thanks to our team members and also our collaborators. Here is our picture photos of our groups. And this talk, most of the work has been carried out by our graduate students, Sung Jung Ho here, and also with the head of the Jiun Sos and also the others. And also I'd like to also thank to our theory collaborators, Simos and Kushik at Harvard and Lund University, respectively. Okay, so my talk, as I showed you at the first slide, is some physics that is relevant to coarsening dynamics in quantum system. In other words, it's like behaviors of non-equilibrium quantum system. So I'd like to introduce some brief backgrounds of how our fields are developed in terms of this phenomena. And then I'd like to introduce our experimental platform, which is strongly ferromagnetic spin-1 Bose-Einstein condensate. And as a main topic for today's talk, then I'd like to introduce our result, that the observations of universal coarsening dynamics in a quenched system, and conclude with talk with some outlooks. Okay, so our motivations is the physics law, discovering physics law in non-equilibrium situations, for example. And by the way, the non-equilibrium situation is quite common compared to the equilibrium situations. For instance, when you prepare your coffee lattes by pouring your milks in the coffee, you can also see initially, after the rite of these perturbations, kind of turbulence behavior in some of this fluid. And after a long time, it becomes equilibrates. And thanks to our nature is so nice that although it looks quite complicated, there are some cases where universal behavior occurs even in the non-equilibrium dynamics, although it's very, very complicated and difficult to trace it out. And one problematic examples are the coarsening dynamics and turbulence. The coarsening means, as you can see in this picture, the two immiscible binary fluids are initially have some small length scale structures, and they grown up is a so-called domain size with a self-similar structure over its time. And very similarly, in the turbulence behavior, this is also the behavior of the wave as a function of time. Initially, you see lots of vortices and small scale structures, but at the long time, you can also see some self-similar structures that reappeared in these cases, which is actually represented as so-called cascade phenomena or Kolmogorov spectrum, which is scaled with k to the minus third. And our question is, of course, if we find this nice feature in classical system, and when very general extensions and expectation is to extend this concept into a quantum dynamics. And the first question, of course, can these quantum dynamics can be also displaced universal? And also, if it is possible, just like in classical system, can we classify the dynamics of the quantum system, especially isolated system without coupling to the large thermal mass or dissipations? So this is sort of main motivations or main question that I like to address throughout this research. And this question is, of course, very, very challenging questions and has long history. And there are ongoing research, and there is a very generic framework has been recently seems to be established, mainly from Jürgen Bergs and the Thomas Kazentsov at Heidelberg University under the name of so-called non-thermal fixed point. What their claim is, when you prepare your initial states, let's say here, and if you drive your system very strongly, and strong means you drive your system very far out of the equilibrium conditions, such that it satisfies these sort of relations. And if that is true, then it can lose the details of your initial conditions, like the microscopic details, like initial states, like spin structures, and microscopic coupling strengths, and just forget about it. And they can collapse into some kind of self-similar behavior, not in the spatial domain, but in the time domain. And this sort of universal behavior has been recently tested. Yes, and this is one example of these numerical simulations where we first create this distributions of which there's some kind of momentum cutoff such that there are no occupations after this cutoff. This is in your state. And after a long time, with some particular models, they find out their relaxation dynamics shows a scaling which can be seen in these numerical simulations. And this kind of physics has been recently can be tested by many different platforms, for example, heavy ion collisions or the universe epsilon inflations. However, as you might know, this is something out of control, our system. Rather, we have a very nice controllable system, which is the ultracold atoms or the Bose-Einstein condensation. And one of the very good, fascinating feature of the cold atom is its high isolation from its environment. And the picture that you see here, this is the glass chamber, and it's very difficult to see, but this faint cloudy shape here is actually the atomic cloud that's trapped by the laser. And we use the most highly isolated material, not material, but we are using the ultra high vacuum chamber, sort of 10 to the minus 11 probe. And also we do not make a direct contact to the system to manipulate them. We rather use the laser or the magnetic fields to manipulate the system. So it's really almost, I would say, a closed quantum system. And of course, what is nice thing is then you can prepare some well-defined initial state, and we can investigate this sort of the time-dependent and the time evolutions of the many-body Schrödinger equations. Of course, it's not usually in the ground state. And one of the pioneering example in our field is about so-called quantum Newton's cradle, where you can create the situations where two atoms are separated at some distance, and they collide and going back and forth and collide many times without equilibrations. Of course, this is something related to the integrable model of the system. And regarding the questions of the universal behaviors, in the long-time relaxation dynamics, there are several breakthroughs using the cold atoms, which observe universal scaling behavior of this dynamics. And the idea is very, very simple, as you might see in this cartoon picture. First, you prepare the atoms in some harmonic trap here, and you rapidly reduce the trap depths in 0.5 milliseconds. The 0.5 millisecond means atom cannot collide within this ramp down seconds. And after that, you close up the trap and wait just a long time. And that's the below picture is a time evolutions of the positions and momentum taken by the atoms. Although it's not so special, but if you carefully analyze their data, they find out that their initial state with the blue mark here, at later time, this curve can be collapsed down into a single universal curve, after long time evolutions, which is actually one of the signature of the universal dynamics that is proposed by the so-called non-summer fixed point. And there are many similar experiments has been carried out over the world. One is the Heidelberg spin-1 experiment, which I will also explain later. And the other one has been recently investigating the 3D Bose gases with some special techniques of homogeneous trapped gases. And all the system, as you can see in this graph, the observables are collapsed down to a single universal functions with a suitable exponent alpha and beta. However, there is something missing in this experiment, which is their experimental exponents, and this unfortunately deviates quite significantly from the theory. For example, in Heidelberg spin chains and the 1D Bose gases, and recent experiment that has been published in the last year also inconsistent with a theoretical or numerical calculation. For example, in 1D gases, you can expect some kind of solid tonic behavior has to be come in, but the model within the solid model does not fully explain this kind of behaviors here. So the natural question that I can ask is then what determines the scaling exponents in this experiment? Will be the appropriate questions. And to that, of course, there's also very interesting scenarios, which is the scaling exponents can be determined by the symmetry of the order parameters and the associated topological orders. And this is the picture of what I mean. Imagine that you have spin-1 system, and spin-1 system, you can imagine it's a spin space. And for example, if you are regions in an easy plane spin-1 axis, then the topological excitation will be, one example is the spin vortex. And if you are regions where your spin axis has only these types of Z2 symmetry, then topological excitation will be the domain work. And depends on which parameter that you quench down in the system. These two peoples have predicted the exponents of beta. I mean, the scaling exponent will be different because of the interplays of topological defects. And today's our talk is focused on that our experimental result is consistent with these types of domain wall mediated universal behavior, which have scaling exponent, which is very close to the 2/3. Okay, before showing the main research, the main experiment observation, let me first explain our experimental platform, just because I guess the modest audience in this conference is solid state of physics. So I'd like to introduce how do we manipulate or what is our system basically so far. And you can find out the detail in this, our result in this paper. Okay, so our platform is so-called the spinel Bose-Einstein condensate. And so I'd like to first explain what is the spinel BC. And the picture in the photos in here is our vacuum chamber. And inside the vacuum chamber, throughout this window, we apply a laser beam. And the laser beam is focused in this way, and they can capture the atomic clouds. And this potential is almost a spin independent, such that atoms has some substructures like nucleus and electron. They are bounded by the hyperfine interactions and forming some spin state. Once a hyperfine spin state at figure 1 and at figure 2. And of course, each hyperfine spin has its sublevels, -1, 0, and 1. The spin 1 I mean here is the hyperfine spin 1, and its subspin space is -1 through 1 cases. And because our potential that trap the atoms is independent of these subspin numbers, you can, yes, and they are in the excited state away from about 1 gigahertz. And because of these properties, they can capture all the spin component with almost the same potentials. So in other words, you have spin degrees of freedom in the system. And also, because they are many-body system, they can collide to each other through the van der Waals interactions. You know, the atoms have van der Waals potential to each other. And in the ultra cold temperature, this sort of potentials can be well approximated to this delta functions type potential, where the characteristic lengths denoted by the AS. And because we have spin degrees freedom, you can imagine lots of scattering channels like spin 1 and -1 collide to each other, or spin 0 can collide to each other. And of course, there are cases where spins are flipped or mixed, so to say, that two spins collide to each other, produce spin 1 and -1, or vice versa. And this sort of van der Waals interactions is actually the scalar one, I mean, the spin independent one. So you can just take into account, I mean, in generally, the scattering rates for this process and that process could be different, right? And in general, we can extend this sort of interactions to take into account the spin independent interactions to writing down in as follows. So you have the first one is the spin independent one, and the second is the spin dependent interactions. And here the F is the spin-on operators. So that is our model Hamiltonians that can describe your system. And our wave functions is now not a scalar, but a matrices or vector, like 3 different components. And what is very interesting here is one can support this sort of spin mixing collision events, which you can also see. People have seen this kind of experiment already more than 10 years ago. I mean, is you prepare the spin 0 state with some finite magnetizations, then as the time evolves throughout these spin mixing collisions, 2 spins are generate to spin 1 and -1 states. And the oscillation period that you can see in this graph is represented by this spin collision rate, which is kind of makes sense, right? How often they can see to each other or mix the spin state here. Please remember that it takes about 100 milliseconds to overgo 1 period at a time. And the second, and then you can immediately see that the ground state of spin 1 condensate can be categorized into 2. One is the ferromagnetic state. In the cases for this C2 coefficients is negative. And in this case for the rubidium 87 atoms. And the other one is the polar cases or the antiferromagnetic interactions, because just because of C2 is positive. And in these cases, the atomic species correspond to sodium atoms. And we have additional degrees of freedom that adding on our system, which is the magnetic fields. And when you apply the magnetic field, this is the neutral atoms. So unlike the electron, they does not feel the Lorentz force, but rather split is energy splitting, like in this way. And here you can see at small magnetic fields, it's linearly behavior with the spin numbers, but you know, it's hyperfine spin state, which means the nuclear spins produce magnetic field, interact with spins and electrons, is coupled to each other. So as some intermediate magnetic fields is no longer linear anymore. So that's representing this in here. And since in our cases, magnetization is conserved quantities, or if you like, it can be a Lagrangian multiplier. So you can eliminate this kind of linear behavior such that you can redraw these pictures on the basis of like this one. Then I can say the quadratic Zeeman energies can be represented like this. I mean, if you have 2 spin 0, then it can be stable energetically compared to spin 1 and -1 state, and is proportional to the magnetic field square. Then you can easily see that the ground state for very large magnetic field will be the 0 spin state, which can compete with the ferromagnetic state. And indeed, because of these computations, it can display a rich phase diagram in the parameter space of the spin-dependent interaction energies and the quadratic Zeeman energies. And this is so-called the energy functional. And for example, as I said, at large magnetic fields here, when Q is very large, then the C2 or the spin interaction energies, your situation will be like that. And the wave function would be all atoms in the zero state. And in the other extreme cases, you can imagine the ground state will be spin up or spin down states. And then I like to introduce our experimental platform. Traditionally, the spin-on beast has been established either these two atomic species, rubidium and sodium. And rubidium is really many to count. I just give up to count many there because there's so many groups in here. And sodium, there are a growing number of groups, but you can also, there are some several groups also in here, including Professor Williamson in Seoul National University. And one specialty that our system, which is lithium-7 atom, is that we have, compared to this system, we have a strongly interacting system. Strongly interacting means if you compare the ratios of the C0 and with respect to the C2, which representing the how often do they collide between two different spin components. Actually, these two atoms, the alkali atoms, is very, very small. It's about sometimes less than 1%. And that's actually the reason why in the previous cases, spin oscillation times takes about 100 milliseconds. And this is basically so-called the scattering length that determines the ratios of the C2 over C1. And you can see that there is no error bars, which means it hasn't been measured before until 2018 that our group have published. And at least in these predictions, the lithium-7 atoms has clear distinctions that has very strong interaction compared to, especially for the rubidium, almost 100 times larger. And the main reason for there is no groups studying the lithium-7 spinor gases is just because different technical steps to achieve quantum degeneracy. But I do not want to explain the details about how we can achieve this one. So just believe that we actually really achieve lithium-7 Bose-Einstein condensate without using so-called the fast-track resonances with sufficiently large numbers, about a few million atoms. And here, one special thing here is that we have chemical potential, or you can consider this one as like bin-field energies or spin-independent energies, about 300 hertz. And we usually trip the atoms in three-dimensional space with laser beam. And the laser beam has, especially for along the z-axis, is very tightly confined, such that the wave function along the z-axis degrees of freedom has been frozen out, so we are in a turgid regions, which is actually seen in this picture. We take the atomic images of absorptions. I will explain it later, but this bright spot means that there are so many atoms, so it's just very, very bright. And indeed, we have tested how strong the interactions are by looking at these spin oscillations, just like rubidium people did. We can see the oscillation time is about only a few milliseconds, like 6 milliseconds in these cases, which is a way stronger than the rubidium atoms. All right. So with this good platform, let me introduce our main result that we explore the so-called domain coarsening dynamics. In order to bring our system in far out of the equilibrium, we first prepare the condensate in some well-defined state and rapidly sweep one of the parameters in here, such that your system are now no longer being in some equilibrium phases. What we do here is we first prepare the polar condensate here and rapidly switching the values of Q in a way that the ground state is the z-axis ferromagnetic and polar condensate is highly excited state. Or you can also make it tune the Q values in somewhere like isotropic point or slightly positive values like this. And otherwise, we rapidly quench the quadratic Zeeman energies such that we can change these order parameter spaces and maybe related topological extension that it supports. At the beginning of this initial dynamics, of course, the domain will form, and it has been already reported in 2006. And this is exactly the same group, same result, that when you first quench the system by reducing the magnetic fields, you see right at the beginning, they see some kind of domain structures are formed and relevant topological excitations. But they do not explain, they do not investigate the long-time dynamics that I would like to show in this graph. But the long-time dynamics is surprisingly is the universal dynamics that's been presented in these pictures, especially when you quench down your system in large negative EQ regions where your order parameter only has these two symmetry. Then you can see only up and down spin domain can happen, and as the time evolves, they will coarse or display self-similar structures. And in these numerical studies, they analyze the so-called spin-spin correlation functions of these types of expectation values with different times, and they find out with suitable scaling, they collapse onto a single universal curve. And this domain grows of t times over 0.68, which is the critical exponent for z is 3/2. And by that, they can say, although this is like closed quantum system that far driven out of equilibriums, somehow it can be same universality classes in model H or binary fluid system near equilibrium dynamics, which is quite surprising even with a driving quantum system. And so our result is to see this kind of behavior in experiments. And that's our experimental apparatus. We produced, in order to produce the atomic gases, we boil up the metal chunk shown in this figure here, and the atomic beam flows here, and we capture the atomic cloud using the laser light in here, and for the cooling down with some evaporative techniques and many others, we can achieve the Bose-Einstein condensate, which can be clearly seen in these momentum distributions. Okay, so the next step is to quench the system. How do we quench the quadratic Zeeman energies? Well, maybe some of you might remember the Q is proportional to the B square. So my question is how we can, going into negative regions, we can do so-called microwave dressing here. The technique is so-called, remember there we have some upper excited state, upper hyperfine state, and you apply microwave that can couple one of these two spin state such that it can repel to each other, and at the end, it can display a negative quadratic Zeeman energies. So our experimental time sequence is as follows. We first prepare the polar condensate in finite magnetic fields. And this is like equilibrium situations. And then we apply the microwave. And as we apply microwave, it means we suddenly quench the system into the regions into the easy axis ferromagnetic ground state, such that the polar state is no longer being in a ground state anymore. And of course, this is domain or motion, so you have to very carefully about to compensate the field gradients. And then you waste some times and take the pictures, and then you get the images like this one. And the picture that we take is so-called absorption images. And in this case, we solve the absorption in situ images. But in simple way, you can imagine that this is atomic clouds in here. Then you shine some resonant light beam. Then you can see some shadows of the atoms because the atoms can absorb the photons. And by how many photons are remaining in these dark regions, then you can estimate what is the density of the atomic clouds. And thereby we can estimate the density patterns of the atomic clouds for each spin state. Okay, so let me show you how the domains emerges when you quench the system. This is our initial conditions. Right after quench, we have almost spin zero condensate period here. There are almost no spin component plus minus one state. And as the time evolves, at the beginning, you see some kind of domain structures that emerges with some kind of micro domains in it here. Just like the early data that you're showing in the previous cases. And the reason for this kind of the spin -1 + 1 state is just because of dynamical, so-called dynamical instability, which means our initial state and the polar state under this negative quartic Zeeman energy is unstable under the very small perturbation. For example, if this is something like the situation where you put your ball on the top of this hill. So even with a very small fluctuation, it can drive the system out of equilibriums. And in these cases, we have spin mixing collision, which is quantum fluctuation, can amplify the spin 1 - 1 state. And one of the very interesting thing still in the initial dynamics, not only for the domain, but there is something analogous to the quantum optics applications. For example, in the initial spin state, when there are macroscopic applications for the polar state, your Hamiltonian can be approximated in this type of pair generation Hamiltonian, which under the time evolutions, it can generate spin secreted states. And within our situations, we are situation in that your initial spin 0 state has large quartic Zeeman energies that the created spin 1 and -1 state can have so-called entangled features or the macroscopic Bell state, which you also kind of observe very similar behavior in the last years. And this times we would like to introduce how such a, imagine, look at this, but this is really high speed or high energy system. And then we'd like to introduce how this and high energy state are equilibrated and display fascinating universal behavior. So we wait more time, 100 milliseconds and 400 milliseconds, and like time goes on. And this is the absorption images, which individual spin components. You can see there's no longer spin 0 component after 100 milliseconds, and that is the magnetization density that is obtained by these formulas, which clearly see that the domain structures are increasing with the system size. And then we analyze these correlation functions as proposed in the theory, and this is correlation functions at different hold time. And in order to rescale this distance, we characterize the domain lengths L. Well, the cases, these correlations are hit the 0 point here, which is basically means, let's say you have two domains up and down, and these two negative points is the point that your distance between the two, and roughly this zero domain is the distance between the end of these two domains. And if you rescale this domain with the lengths here, it beautifully collapses down into a single curves in here. And we can plot these dynamics of the domain as a functions of time, and it looks like this. And we compare our friends, theoretical calculators, without any fine tuning. We are currently doing some fine tunings, but without fine tunings like particle losses, we find out very good agreements with these numerical simulations. Of course, the next step is to extract the exponents with certain reasons that you choose a reasonable basis. We find out that our exponent is about 0.6, which is about smaller than the theoretical predictions in numerics, which is about 0.66. And to account for that, we take into account our finite imaging resolutions because nothing is perfect. So we have finite imaging resolution, as you can see here. We can imprint a so-called the spin spiral state, spin up and down in spiraling state, which decomposed into 3 spin state. Then you make the cross sections and plot its density profile, and you see it has some finite contrast because of finite imaging resolutions. And it turns out the best resolution that you can explain this kind of fringe is about 5 micrometers, which is saying makes sense based on our imaging, the numerical approach of our imaging system. And so we apply as the Wiener deconvolution method, and you observe a little bit of enhancement, not that much, but a little bit of an enhancement of critical exponents, about 0.6. A little bit of disappointment, but we find out that the numerical simulation has been performed with extremely large system size. I mean, here the system size about 800 times of your spin healing length. So we put some number in our experimental parameters. For example, the spin collision time denoted as TS is defined in this way. And remember, this C2n is spin interaction time. We are very strongly ferromagnetic interactions that gives us our unit time is very, very fast. It's about 500 milliseconds. And our spin healing length is about 2.1 micrometers. So our parameter range is about here. So where we are looking at these small windows in here, not the entire regions in here. And also these papers also investigate the kind of the finite size effect, where they say when this system size is not good enough or large enough, this critical exponents has to be deviated away. And if we just extrapolate this curve in here, maybe our point is something around there, which is not very far away from our experimental observation. So maybe we think we have to check out this one in numerical simulations, but we might limit it by our finite system size, which in some sense is not such a surprise. And then the next step is to check out whether the system is really universal, means that it's independent of some initial spin configurations. For example, we can prepare some different initial spin state with not in a polar state, but superpositions of 1 and -1 state. Or you can more strongly drive your system, drive more strongly by stirring your system, by stirring the laser to create vortex and anti-vortex pairs in here. And for the 1 and -1 cases, which I denote antiferromagnetic spin initial state, it has a different dynamical instability. Apologize for the technical jargon, but it basically means that instead of kinetic energy burst mode dynamic instability that I showed you before, it is something like immiscible nature because of strong spin immiscible interaction, such that when you time evolves, instead of a jet-like structure, we observe the immiscible nature, but still it displays a very good self-similar structures of the long-time evolutions. And we perform the same sort of experiments, like investigating correlation functions and scaling, which finds out very similar exponents, which is also obtained after the deconvolutions. And this is also same for the mass flow cases when we perturb our system, the our system. And one interesting thing, motivation to this is there are some kind of interesting remarks on the mass flow and the dynamical critical exponent, which means when you force, numerically, when you force your system to have no mass flow, then you find out the critical exponents to have about 1/3. And if you include mass flow, then you can have up to 3/2. So we want to really make sure that because our imaging resolution is not enough to identify these so-called vortices. By the way, this is not the in situ, I guess. This is the time of flight images. To support that our system indeed is faraway system, and although we cannot measure experimentally the mass flow, there is clear evidence of the mass flow that injecting vortices in the system. And by doing the similar stuff, we also obtained very similar result that we have obtained in the previous cases, 2 different states. So by that, we have up to now 4 different, we compared 4 different energy conditions. First, these 2 data point is the same initial state with the polar condensate, but with different quench. One is the -200 Hertz, right? The other one is -120 Hertz. And the other one is strong perturbation with polar condensate, and the other one is the different spin conditions. All the exponents are around 0.6, where the thermodynamic limit predicts about 0.7, but it clearly deviates from the other exponents, for example, the 1/3 or 1/2, which is the case for belongs to different universality classes. Oops. And yes, and also we have very interesting, maybe very interesting structures in the domain, which is in a very long time, because there are no longer domain in system. There are only 2 domains, spin up and down spin state. And we can also take an images not along the vertical axis. We can also take, by rotating spin, for example, in horizontal axis, then you can decompose what is the magnetization along the x directions or y directions. And of course, the contrast is reduced because you cannot guarantee your rotating axis is actually aligned with your imaging axis. So that's the reason why it's not saturated one, but it doesn't matter. It pointing out that this domain or at the interfaces is like rotating in like that way. So which is called the block domain wall type. This is the most cases, but in some cases, like 30% or 20%, I had to check out the statistics, but in some cases, we find out that the MX, sorry, this is the MX, not the MZ, has different signs, which means that it points in the upper part, it points in the plus x directions, in the long part, it points in the down directions, and which means that naturally you can imagine that the domain will look like, because there's spin down up and spin down here, and in between there's a domain where and the spin axis has to be opposite directions. So maybe it's some kind of spin rotating axis can be happens in here. Although we cannot prove this one, maybe this kind of one interesting structures that composite topological structures of domain or spin vortex, maybe the soliton, which is not sure, but it could be very interesting. But I guess this could be only quite supporting evidence there is a kind of mass flow exists in our experiments. Otherwise, it cannot be done. Okay, I think my talk is ended a bit earlier, but let me introduce our ongoing work. Because I said at the beginning of my talk, our motivation is to identify the critical exponents and to explain or to associate the critical exponent to the order parameters and relevant topological excitations. We can also do some different quenches, for example, Q equals 0 point, because at Q equals 0 point, at the symmetry of the order parameter is SO3, so you can have any different directions. And it predicts, sorry, I should put the references. In numerical simulations, because of the vortex pair are bind together, it slows down this dynamics such that the domain grows about 1/2. And this is our preliminary experimental result. We vary these strengths of the Q values here and measure the same type of experiments. And especially for the 0 cases, in contrast to the GIS cases, domain wall collapsing actually happens not only for the spin magnetization along the z-axis, but also transport axis. And Bose gives around about 0.5, which is of course smaller than 0.5, but it's kind of around 0.5 values. And so the next thing would be, can we associate something like the topological structures like vortices at this Q equals 0 point? And if we can find out some evidence, then I think maybe this could be very supporting evidence that these topological excitations can determine the critical exponents in this is far out of liquid dynamics. Okay, so sorry, I think I have made my talks a bit fast, but so this is my conclusions. We have investigate our universal dynamics, and there are of course very interesting ongoing works like domain war dynamics. For example, if you apply some gradient forces between two domains, there are some proportions that some kind, maybe you can expect some fractional square or soliton-like domain wars, and sometimes in one-dimensional system, interesting solid dynamics can be also happens, which can be investigated in the following years. All right, so apologize for my time, and to the end, thanks for your attentions.
Okay. Thank you very much for the nice talk. It's a very, very beautiful result. Congratulations. Okay, we have a short time for 1 or 2 questions. Yes, Hyung-Sun Choi, go ahead. Yeah.
Well, thank you. Very interesting. So the last part of your talk, you had this domain wall magnetization image along the x-axis. So can you do that imaging while this coarse graining is happening instead of at the last minute? So that to see how that domain actually evolves.
Yes, that's very good question. Yes, we haven't investigated. Yes, that's very good questions. We have only few images, and interesting picture. We have seen very interesting pictures that some Lett's domain wall edge and light domain edge are spreading over, and they seems like to meet and annihilate it. But unfortunately, this is just when you take these images, it's disruptive images. So we cannot like take these images and so forth. We cannot trace its time evolution, unfortunately. But yes, we should have a look at it. Thanks for the comment. We should have to look at it and think about which kind of interesting comment that we can draw.
Okay, thank you.
There's yeah, last question is Kwon.
Okay, yeah, thank you very much for your talk. And I'm just wondering, like, you were talking about reaching the isotropic point, and I have been wondering, like, were you able to reach isotropic point in 2 dimension? I mean, and if that's so, I mean, were you able to see spin disordering?
Let me rephrase your question. Okay, because I'm experimentalist, it seems like, how can you guarantee this is really isotropic? Like Q equals 0, maybe Q equals 0.5 or 0.1? Well, is it your questions?
Well, I mean, and also if you're able to reach this point, isotropic point in 2 dimension, I mean, you should not have any kind of like spin ordering.
Yeah, exactly.
So I'm just wondering, like,
exactly. This exponent is not only extracted by the magnetization along the z-axis, but also the x-axis. Yes. Of course, we are not sure about this really isotropic exactly Q equals 0, but one has to compare your spin-dependent interaction energies, how you're deviated from your spin-dependent interaction energies. We have to think about what is error budgets, but maybe we are not that deviated much, let's say 1% or 2% to these isotropic points. And of course, that could be one reason for these such kind of deviations of 1/2. But yes, we have to check.
Okay, thank you.
All right, thank you very much for the nice talk again. Yes.